This is lesson number 3. The introduction was the first lesson about acids and bases in solution. And a question is often asked, what if you put a salt in water? Will that change the pH? A common misperception is that since a salt is not an acid nor a base, a salt in water should give a solution with a pH of 7. And that conclusion would be incorrect. And you'll see why in just a minute. You'll notice that from the previous chart in the last lesson, there are a lot of cations and anions that can behave as acids and bases. For example, in this case, if we have the carbonate ion with its -2 charge, because it's a -2 charge, it can attract a proton with its positive charge. And I would suggest that in order to help you, at least early on, understand something called hydrolysis, which I'll comment on in a minute, it's very convenient and helpful to write the water molecule as HOH, as the combination of a proton, H+, and a hydroxide, OH-. Because now you can see that this proton is going to be attracted to the negative ion and is going to leave behind a hydroxide. So when the carbonate picks up the proton, it becomes the bicarbonate ion, and instead of having a -2 charge, it now has a -1 charge. Meanwhile, since the water molecule lost its proton, what's left behind is a hydroxide with its -1 charge. This process is called hydrolysis. And we say that the carbonate ion has been hydrolyzed. The carbonate ion has been hydrolyzed. This terminology is going to be very important when we get to chapter 18. But the bottom line is, if I can erase all of this, the bottom line is the carbonate ion, when it's in a water solution, will hydrolyze to produce a solution with a pH that is greater than 7 because of those presence of hydroxides. And you might say, well, how do you put a carbonate ion in solution? Well, you would do that by putting a substance like sodium carbonate or potassium carbonate, where the sodium and the potassium ions would act as spectators and not affect the pH at all, because the conjugates of strong bases do not hydrolyze. Now, another example that's a little more complicated is this metal cation that you see right there. It's a cation because it has a positive charge. But you've never seen one like this. These are called complex ions. There is a whole chapter devoted to a discussion of these towards the end of the book. And these complex ions are actually metal cations that are surrounded by either molecules or ions. In this case, your aluminum is surrounded by 6 water molecules, one above, one below, and then this would be in the North Pole, this one would be in the South Pole along the axis, and then the other 4 water molecules would be equatorial water molecules, located around the equator, if you will, the 4 points of a compass, for example. And as a result, you produce this complex ion. Now, because of the fact that water molecules do not have a charge, the original +3 charge of the aluminum ion is maintained. And because it has a +3 charge, a positive charge, it can attract a negative hydroxide. Or another way of looking at it is because it's got water molecules, and this is more important, it can donate one of these protons from one of the water molecules to your water, and instead of having H2O, it'll become H3O plus. And instead of having 6 water molecules, it's down to 5 intact water molecules. And the one water molecule that donated a proton leaves behind a hydroxyl group, OH, and it's gone from a +3 down to a +2 charge as a result of that negative hydroxide that's left in the complex ion. The bottom line is this. This complex ion in solution is going to produce an acidic solution with a pH less than 7. And you might say, well, how do you put a complex ion into solution? Well, this complex ion would have as its anion the conjugate of a strong acid, like chloride or nitrate. These are the conjugate bases of strong acids, and they would be spectators when you put this complex ion into solution. Now, moving on, our bullet points. Anions that are conjugate bases of strong acids, like those, and cations that are going to be the conjugate acids of strong bases, are not going to affect the pH at all. They won't hydrolyze, they'll have no effect. However, there are lots and lots of basic anions, which are the conjugates of weak acids. And all are conjugate bases of weak acids, and therefore they are going to affect the pH and cause the pH to be greater than 7, like we saw up here in this example. Some vocabulary words in the next bullet point. If you have a polyprotic acid, like phosphoric acid, that we talked about in an earlier discussion, this has up to 3 protons it can donate. Each time it donates a proton, it deprotonates. D means to remove a proton. And if you have something like the bicarbonate ion from carbonic acid, the bicarbonate ion can either pick up a proton or it can lose a proton. So we would say it's amphiprotic, which means it can go either way. So if we look at some of these examples, here you see the conjugate bases of strong acids. Conjugate bases of strong acids. And they're not going to affect the pH at all. Down here, you have the conjugate acids of strong bases. In other words, you have what's left behind when the strong base has received a proton, and as a result, it's going to not affect the pH because the conjugates of strong do not hydrolyze. Conjugate bases of strong acids don't hydrolyze. Conjugate acids of strong bases don't hydrolyze. Over here, you have the conjugate bases of weak acids. And the conjugates of weak hydrolyze. And so therefore, they will affect the pH. Your complex ions will affect the pH as well. Here, you have some conjugate acids of weak bases. By the way, they can also act as weak acids and donate a proton. But in this case, they're going to affect the pH. And the pH, because they produce hydronium ions, because they can donate a proton, and that'll be picked up by a water molecule to make a hydronium. Those hydroniums will cause the pH to go down, and your pH will become less than 7 acidic. And the same would be true for these things. So, looking at the bullet points again, alkali metal and alkali earth cations have no measurable effect on the pH. Right there. Here are your cations from alkali metals, cations from alkaline earth metals. The basic cations are conjugate bases of acidic cations, and therefore they can make the solution basic. And then down at the bottom, up here, the metal cations with +2 and +3. In this case, we're talking about aluminum, but often we're talking about transition metals as well. They can be at the center of one of these complex ions. So we ask ourselves this question. If we put sodium nitrate into solution, will it affect the pH? Now, the sodium nitrate might have been mined from someplace in the earth, but we're going to pretend in every case that each of these salts was made by an acid-base reaction. So the question is, what acid and what base could be combined to make sodium nitrate? And if you think about it, a base such as sodium hydroxide and an acid such as nitric acid could make sodium nitrate. The hydroxide and the hydrogen would make water, and the sodium and the nitrate would make sodium nitrate. Acid plus base makes salt, here's your salt, and water, here's your water. Now, sodium hydroxide is a strong base. Nitric acid is a strong acid. Strong plus strong produces a neutral solution every time. It's a neutral aqueous solution, pH of 7. Now, what if we have a salt like this one? Let's pretend again it came from an acid-base reaction. The base could have been potassium hydroxide, and the acid would have had to been phosphoric acid. We have a strong base, we have a weak acid, strong wins. The strong base wins, so the pH is going to be greater than 7. What about the next one? What about iron chloride? Iron 2 chloride. Where could we get the iron from? What base? FeOH2. Because it's iron Roman numeral 2. Where could the chlorine come from? The chlorides. Hydrochloric, strong acid. We have a weak base because it's not one of the bases you had to memorize. We have a strong acid. Strong wins. pH is going to be less than 7. What about up here? Where could that sodium come from? A strong base. Where could the bicarbonate ion come from? Carbonic acid, a weak acid. Strong base, weak acid, and as a result, if we look ahead on down here, the pH is going to reflect the strong base and be greater than 7. Finally, here, the ammonium could have come from the weak acid ammonia and picked up the hydrogen ion, acting as a Bronsted base. My fluoride could come from the weak acid, hydrofluoric. We have a weak base. We have a weak acid. Which one wins? And you might think, well, this will produce a solution that has a pH of 7. That would not be correct. If we look over here, looking at letter D, this is going to be slightly basic, but look at letter E. When we have a salt that could be the result of a weak base plus a weak acid, in order to determine whether the solution will be acidic or basic, we have to look at the Kas. In this case, my Ka is greater than my Kb. My Ka is bigger than the Kb. Therefore, Ka wins. It's going to be slightly acidic. If the Kb were bigger than the Ka, then the Kb wins, the weak base wins, and the solution would be slightly basic with a pH greater than 7. And that is another test question. All right, predicting the direction of an acid-base reaction. And here's the rule. Reactions are always going to go from strong to weak. If your acid and base is stronger than the conjugate acid and conjugate base, the reaction will go to the right, strong to weak. But if my conjugates are strong, I look on the chart and I see that the conjugate acid and the conjugate base are stronger than the acids and the base that they came from, which are weaker, then the reaction goes to the left, from strong to weak. So you have to look up the acid and its conjugate acid, or look up the base, and right across from it will be its conjugate base, but they will always agree with each other. You will always go from strong to weak. You will never have the acid going towards the conjugate acid, but the conjugate base going in the opposite direction towards the base. They will always agree. You just have to look at the acid and its conjugate acid, or the base in its conjugate base. And that's how you know whether the overall reaction will be product or reactant favored. If it goes from strong to weak in this direction, it's product favored. If it goes from strong to weak in this direction, it's reactant favored. Now, sometimes you can tell without looking at a chart. For example, here you can see a strong acid. So automatically you know if the strong acid is on the left, the only direction it's going to go is to the right, and it's not going to go to the left. In a situation like this, you're going to have to look them up on the chart. And you're going to see, in this case, the reaction is going to go from the stronger, which is on the right side, to the left. So this is going to be reactant favored, and my value of K is going to be smaller than 1 because the denominator with the reactants in it will be bigger than the numerator with the products in it. So you'll need that long chart in order to answer the question, which way does this reaction go?